Okay, thank you, Todd. So let's just get right into it. As many of you know, we have a lot of the expert packagers and developers of Spack assembled here in the room. So a lot of you know that if you want to create a Spack package for a repository, it obviously involves understanding the build system of the repository you're trying to convert into a package.py file. And if you've done this a lot of times and you're doing it for a new package or new repository that someone asked you to package, that can be a relatively simple process because you have this sort of built-up understanding of how build systems map to the concepts that Spack provides to you. So it can be a manual process depending on your level of expertise, can be a bit more automated if you know where to look. And obviously this is like a perennial issue, but software is evolving at a faster pace than maintainers can keep up, whether this be for core utils, Python packages, etc. The amount of effort involved in actually adding a new version, adding new variants, etc., can be involved in, depending on the amount of packages that you want to maintain, can lead to outdated packages in the built-in repository. This sort of dovetails with the fact that LLMs are happy to write code. Notice I'm not saying that they're great at writing every single piece of code, but they are happy to write it if you give them some sort of instruction. And they also learn from feedback if you provide it in a way that is actually beneficial to the way it understands certain paradigms. So in my journey of trying to understand how LLMs, I'm using LLMs and sort of coding agents interchangeably here, but you can sort of think of the way that they think about Spack packages is sort of in a brute force manner. If you tell Claude Code or Codex, here's a repository, create a Spack package for it, you're within the context of the Spack packages repo, it actually does a pretty good job of understanding, okay, I need to use these certain commands to find repository metadata, look for licenses, look for cmakelist.txt, sort of find out what abstractions in those build system metadata are necessary to put into a package.py file. And it'll try to even look for existing packages with certain keywords. I will say the keywords aren't amazing. If you give it the name of a GitHub repository, it'll just use GitHub, the organization, and the repository name and look for other packages that have those keywords, which obviously isn't amazing. But you can see it's sort of getting to a place where it understands it's in this repository context, and there is other information available there that can help it with this current task, generating a package file for a brand new repository. So I think it's trending in the right direction, but I think that they don't necessarily have this sort of innate understanding of what it takes to bridge the metadata that the user is potentially giving them with the semantics that you actually need to create a successful Spack recipe. So what goes wrong here? I'd say the number one issue is that they don't really understand that Spack has a sort of transitive nature to it. It will, you tell it to generate a package for a repository, and it will, look through CMake files, look through make files, etc. And it understands if you give it the right instructions, and sometimes natively it'll understand, okay, this is a dependency that I can put into the package.py file. These variants look like they're sort of attached to the find package CMake line. I'll add that in there. But they don't inherently go and check whether or not those variants actually exist in the packages that they're depending on. So it sort of gets to this struggle where they will create the package.py file and not really go and verify whether or not all the information that they wrote is grounded in truth, I would say. And it gets to this bigger issue of them treating any metadata or any information that's in Spack as sort of this irrefutable truth that can't be questioned. So, it's sort of build system files are written by humans, package.py files are written by humans, and it sort of has this thinking that it can basically refer to any of that metadata and not sort of critically think about whether or not it's correct. So it'll encode whatever you give it, which is not really a surprise, but it'll take whatever you give it, not really question it, even if you ask it to question it, and sort of put that in the package.py file and just call it a day. And right now I'm just talking about default behavior of these coding agents. I'm going to get to what you can actually do to sort of mitigate this behavior later on. And then a pretty big issue, a lot of the time with these coding agents, as I'm sure many of you are aware, if you're operating in the context of a repository, the way it sort of finds feedback signals can vary, depending on your instructions. If you tell it to compile a package or something like that, the output from GCC can be quite helpful sometimes. Uses commands like grep and things like that to basically find whether or not the output that the program it's trying to improve upon is actually working. And this sort of becomes a problem when the feedback signal that it gets isn't really interpretable. So a lot of the time you get, X is unsatisfiable, which I'm sure is extremely frustrating to a human as well. But the LLM basically, because this is such a broad issue, can't really figure out what to do next. So sort of finding out what the right initial context you need to give it and what signals, once it actually errors out, is pretty crucial. So we came up with like this sort of evaluation pipeline. It's not really a production system to generate Spack packages, but it was more to understand which levels of information are needed to find out where models succeed at generating these packages. So we built a couple different tools like to extract different levels of repository metadata, look in that repository metadata and match on certain keywords to find existing Spack packages. So if you're writing like a CFD solver or something like that, you might expect that a lot of the dependencies have a good amount of overlap, like CUDA or HIP or OpenMP support, and it's probably a better idea to give a package that has those already implemented as an example rather than a random, Python file. So those are the sort of things that we were thinking about, and you can ablate all these features to find out, when you introduce new information, what is the most beneficial over time. And we weren't only looking at sort of installation success or concretization success. We wanted to think about, how the LLMs actually create packages that are going to be useful to the community. So sometimes we would see the LLM, you give it a tarball, you give it a Git repository, and it would just create a stub, like it would say like CMake package and then set the URL and call it a day, which a lot of the time will work, but obviously it's not really useful to anyone else because there are no variant set, there's no dependencies. And we wanted a way to sort of evaluate how the LLMs are including variants and optional dependencies. So we did some of that in addition to just baseline installation success. So this is, when we wrote the paper and the evaluation pipeline, the models were a lot older than they are now, but I would say not really that crazy of a statement to say, but the capability of the model is sort of the determining factor in whether or not it creates Spack packages well. But what you see is that if you combine the sort of iterative loop where you tell it to generate a package, you have it access, you tell it do Spack list to text syntax, do Spack spec to do concretization, and then Spack install, and sort of do that in a loop, in combination with these sort of references that give it an idea of how other Spack packages are written, you get a pretty substantial improvement over time. And I wouldn't be surprised if you use newer models that this would be even better. So what we found that helped LLMs write packages is sort of not allowing the LLM to go like look through the entire cmakelist.txt files or all the make files within a repository. Obviously, it can look in there, but it can't. We don't want it to like actually interpret everything in there. We wanted to give it some heuristics about how Spack thinks about certain CMake commands. The Spack package examples really helped. This idea of just allowing it to do iterative validation and repair with the signals it has access to was pretty helpful. We did a small experiment to find out like whether or not the Spack audit command in between sort of the package generation step helped a lot. So it's sort of, and this is something I'm going to mention later on, but I think that if you're looking at this from the perspective of a new user, it's more helpful to like go into one of these coding agents, ask it to do something in a Spack context, and then see how the coding agent behaves, because a lot of the time that's going to mirror how a junior person is going to tackle the problem. A lot of the time it's not because they go down these pretty stupid rabbit holes a lot of the time, but I'd say if you're more of a Spack expert, it's a lot easier to sort of find out where the LLM is going wrong and correct it. But I think it's useful to guide them so they can be more efficient and sort of make them more capable for more junior people who aren't necessarily well versed in how to correct Spack. And this is something Harmon mentioned a couple weeks ago, but something that he's found, and I've also found good success in, is that they need to be grounded in reality. And it's sort of back to this idea of them trusting build system files and existing Spack references a little too much, and that they should be attempting to actually build the package before they actually translate all the information they have in the repository metadata directly to a package.py file, just to sort of ground their experience in reality and provide feedback that maybe what is in the cmakelist.txt file is not really what you need to have a successful Spack recipe. So I'd say, they're pretty capable. They just need like some structured guidance to perform reliably. It's nothing like too wild. And something that I've been experimenting with, and Harmon and Wolter have been working on too, is sort of taking these small nudges that you need to make these LLM workflows with Spack more successful. So there are these things called agent skills, which is essentially a markdown file that you can give like a small summary to a coding agent to sort of tell it, this is what this task can do, and these are the sort of instructions you need to actually follow it. And if you are sort of including the information that I talked about before, like some heuristics about how to map different Spack concepts between each other, you can sort of enable these different workflows that are manual right now, but should be automated. Should be able to be automated, like bulk package updates, maintenance workflows, like introducing CVE fixes. And I'm planning on pushing the skills that I have for like this new package generation. That could be helpful. But the idea is to sort of make this expert packaging guidance accessible to people who are newer to the community. And it sort of also gets to this idea of, if we have all these people who are wanting to use Spack for packaging, but are using LLMs to write the package.py files without sort of the best practices that we want, we can really inundate the existing reviewers with really bad package.py files. And there are some ideas about how to actually mitigate that, but like you can ask the LLM ask the user to ask the LLM to justify their decisions with evidence every single time. You can enforce disclosing LLM usage for each PR. But at the end of the day, it's going to be a pretty hard issue to actually mitigate. So I'd say they're pretty great assistants with some slight nudging. These shared instructions can really help encode the best practices. I think more complex workflows like MCP servers, or like a custom coding agent that you sort of package together to do this one workflow, can introduce a lot of maintenance burden. And I think these skills, because the LLMs are already so capable at understanding Spack, I'm not going to say that they're inherently able to think about Spack in a way that a lot of you might be able to, but with some small modifications, they can get to a place that sort of approximates that. And like I mentioned before, iterating with these LLMs from like the perspective of a newer user can reveal a lot of opportunities to improve like Spack's interfaces. So, yep, that's all I have. Got a funding acknowledgement here, and then the paper that we wrote, where we did a lot more experimentation in what signals were most useful, is available there. And thank you.
Okay, any questions for Caetano?
Hey, thanks so much. Did you try mixing in bespoke MCP servers for specific packages and documentation?
A bespoke, sorry, I missed that.
MCP servers for example, we had the similar experience as you report with writing, for example, write me an input set that can model the greatest laser plasma experiment. But once we mix in like an MCP server like Context 7, who's like a RAG trained just on code snippets through the whole example, things usually get significantly better for us, at least for hallucinations.
Yeah, I mean, I think, so MCP servers are a little complicated. I think that they can be useful for certain tool calls, like maybe finding examples would be great. But I think if you're trying to create like this overarching MCP server that generates Spack packages for you, sort of the workflow diagram gets a bit complicated, but I agree. Like for certain tool calls, they can be very useful to actually retrieving context that someone might want in their context.
Yeah, specifically you get like the latest examples and not like something it was trained on.
Yeah, totally.
Other questions?
So it seems like you use the models for greenfield new packages. What about doing things like adding new versions, checking out the CMake to see what the new options are for those packages, and then like modifying an existing package?
Yeah, so we did the greenfield package generation to sort of create a better evaluation framework. But there is a PR up that Walter worked on and I have helped with to basically do that and use some of the instructions, like some of the heuristics that I talked about, to actually make that happen. So I think it's an easier problem because they already have some sort of idea of how the existing package was implemented, and if you sort of combine that with the ideas to sort of constrain the LLM's thinking, it can be a good way to do that. So.
Okay, one more question while John gets set up. Anybody? I have a question. How are you going to teach these things to know, like, that certain variants, like how to verify variants, or where in the code to look for verifying variants, like how to understand the names, which ones are correct, which ones exist, which ones don't, and that those things fundamentally come from the build and from like the build tarball? Like, what's the way to verify that? Could you make it write tests? Is there something else?
You can make it write the test. Like a lot of the time, it's just some sort of manual validation. Like I have it, generate the list of variants from like a cmakelist.txt, which is not, going to get every variant, but then you can have it sort of toggle each one and see whether or not it succeeds.
Do you think it would help if we had more audits for packages that could like tell the LLM that like these things are wrong with it? Like,
yeah, I mean, I think that would be an improvement, like not only for a human, but for the LLMs. Just they need like more direct signals for like what they're generating is like completely not based in reality.
Okay.
So.